Hello everyone. Welcome to SHR Trinity. In our previous video, we explored zero-shot prompting. Today, we advance to the next critical technique, chain-of-thought prompting. In this video, we will cover the foundational interview questions on chain-of-thought prompting, explaining how providing just a. Before we begin, if you're looking for practical, industry-oriented training in artificial intelligence and generative AI, SHR Trinity offers a comprehensive 30-hour training program. For complete course details, check the description below. Now let's begin today's interview session. We will now begin with the interview questions for Chain of Thought Prompting, Part 4, Tree of Thoughts and Systematic Search. Moving on to our next question, what is Tree of Thoughts, CoT, prompting and how does it extend chain of thought?
Welcome everyone. Today, let's unpack Tree of Thoughts, or CoT, and see how it revolutionizes standard chain of thought prompting. When we use traditional chain of thought, the model reasons linearly. Think of it as going directly from step 1 to step 2 to step 3. But what happens if the model makes a mistake at step 2? In standard linear prompting, it gets trapped and hallucinates a flawed outcome. CoT solves this by converting problem solving into a decision tree, very similar to how a computer evaluates chess moves. At any given point or node, the model generates multiple candidate next thoughts, evaluates how promising each thought is, and chooses which branch to explore further. If it realizes a specific path leads to a dead end, it can backtrack to a previous step and try an alternative route. This is essentially merging the semantic generation power of LLMs with classical computer science search algorithms like breadth-first search or depth-first search. Let's look at a concrete example, solving the game of 24 math puzzle. In this game, you're given 4 numbers and must use basic arithmetic to reach 24. With CoT, the model proposes several initial arithmetic combinations. It evaluates each remaining set of numbers. If a branch produces a number that makes reaching 24 mathematically impossible, the framework discards that branch, backtracks to the previous node, and tries a different mathematical operation. This structural ability to explore, evaluate, and backtrack is what makes CoT dramatically superior for complex, multi-step problem solving.
Moving on to our next question, how does Tree of Thoughts enable exploration, backtracking, and look ahead in LLM problem solving?
Let's dive deeper into the key mechanisms that make Tree of Thoughts so powerful: exploration, look ahead, and backtracking. In basic linear prompting, an LLM generates tokens sequentially. If it makes a wrong turn early on, it has no native mechanism to say wait, this isn't working, and start over. It's trapped in that bad branch. CoT changes the game by introducing 3 distinct operations. First, exploration. At any decision point, the system generates multiple candidate thoughts, giving us several potential directions to investigate. Second, look ahead. The model evaluates the state of each branch to project whether continuing down that path will likely lead to a valid final solution. Third, backtracking. If a candidate branch gets scored poorly or hits a dead end, the system discards it and steps back to the parent node to try a different candidate branch. It's crucial to understand that an LLM cannot do this entirely inside a single standard prompt call. It requires a programmatic controller, typically a Python script, that manages the loop, makes callouts to the model, and tracks the overall tree search state. Consider a practical coding example where you're asking the model to construct a complex software module. Branch A attempts to build the feature using object-oriented inheritance, but the evaluator scores it low due to rigid dependency coupling. Instead of continuing down a broken path, CoT backtracks to the root decision point and launches branch B, exploring functional composition instead. This systematic mechanism guarantees far higher reliability in software engineering and planning.
Moving on to our next question, what are the core components of a CoT framework: thought decomposition, generation, evaluation, search?
To build or understand a Tree of Thoughts framework, you must master its 4 foundational pillars: thought decomposition, thought generation, state evaluation, and the search algorithm. Let's walk through each component step by step. First, thought decomposition defines what actually constitutes a single node in our search tree. Depending on the task, a node could be a single line of code, a math operation, or an entire paragraph. Second, we have the thought generator. Once a node is established, the generator prompts the model to propose candidate next steps. Third comes the state evaluator. This component acts like a judge, inspecting each candidate node and assigning a score, for instance, a rating from 1 to 10 or categories like sure, maybe, or impossible. Fourth and finally, the search algorithm, such as breadth-first search or depth-first search, uses these evaluation scores to decide which path to expand next and when to backtrack. If your evaluator prompt is poorly defined, the entire system breaks down because it will score bad paths favorably and waste compute on dead ends. Let's look at how this operates in a creative writing application. Suppose we want to write a coherent long-form article. The framework decomposes the task into paragraph-level nodes. At the first node, the thought generator outputs 3 candidate opening paragraphs. The state evaluator rates each candidate's tone, clarity, and logical flow on a 1 to 10 scale. The search algorithm picks the highest-scoring candidate paragraph to build upon, expanding that specific branch into the next section of the article. That is how all 4 components work in harmony.
Moving on to our next question, how do search algorithms like BFS, breadth-first search, and DFS operate over LLM thought trees?
Now let's talk about the algorithmic engines driving tree of thoughts, search algorithms, specifically breadth-first search, BFS, and depth-first search, DFS. When we organize thoughts into a tree, we need a systematic rule set to determine how the model navigates that tree. BFS works level by level across the horizon. It generates and evaluates all candidate thought nodes at the current depth before moving on to depth layer +1. This approach is fantastic when you need a comprehensive global perspective and when the total tree depth is relatively shallow. On the flip side, DFS picks a single candidate branch and dives straight down as deeply as possible until it reaches either a final answer or a complete dead end, at which point it backtracks. DFS shines when memory compute is constrained or when you just need to find any single working solution as fast as possible without comparing every alternative along the way. In enterprise AI engineering, the most common variation of BFS is beam search. In beam search, rather than keeping every single branch open at depth level n, we keep only the top B most promising nodes, known as the beam width, and discard the rest. Let's see how this works with an example. Imagine generating a complex technical document layer by layer. Using BFS with a beam size of 2, at each chapter section, the LLM generates multiple drafts, evaluates them, and keeps strictly the top 2 best performing paragraphs. It then expands those 2 branches into the next layer. This keeps our memory consumption tight while ensuring high quality across the document.
Moving on to our next question, what is graph of thoughts, GOT, and how does it allow nonlinear thought aggregation?
Let's elevate our discussion from trees to graphs by looking at graph of thoughts, or GOT, introduced by Beste and his colleagues in 2023. While tree of thoughts was a major leap forward over linear chain of thought, tree structures still have a key limitation: branches can only fork outward or backtrack. They can never merge back together. Graph of thoughts removes this restriction by modeling reasoning as a directed graph. This allows for arbitrary network connections, enabling 2 powerful new capabilities: thought aggregation and feedback loops. Aggregation means taking 2 completely independent, successful thought branches and merging their insights into a unified node. Feedback loops mean taking a downstream thought and feeding it back into an upstream node to iteratively refine an earlier concept. However, keep in mind that this added power comes at the cost of high software engineering complexity. Managing dynamic graph states and node dependencies requires robust infrastructure. Let's walk through an intuitive example: sorting a massive dataset. In a graph of thoughts pipeline, the input array is split across 4 distinct thought branches. Each branch independently sorts its subset of the data. Then, using a merge graph operation, GOT combines these subsorted arrays pairwise, aggregating the intermediate graphs until a completely sorted final array is synthesized. This nonlinear, multi-branch synthesis is something standard trees simply cannot perform.
Moving on to our next question, How do you design an LLM-based evaluator to rate intermediate thoughts in a CoT search?
A tree of thoughts framework is only as smart as its evaluator. Today, let's explore how to design an LLM-based evaluator to rate intermediate candidate thoughts. When we build an evaluator, we write a meta prompt that instructs the model to step into the role of a strict, objective judge. The prompt passes three key pieces of information: the ultimate goal of the user, the sequence of thoughts taken so far, and the specific candidate thought currently being evaluated. We can ask the model to evaluate this candidate in two main ways: using continuous scalar scoring, like a rating from 1 to 10, or using categorical classification, like labeling the step as sure, maybe, or impossible. In practice, categorical evaluation usually works better. LLMs tend to be inconsistent when assigning precise numerical scores, but they excel at placing items into clear, qualitative buckets. It's critical to calibrate these prompts carefully. If your judge is too lenient, the search algorithm will waste huge amounts of compute exploring flawed branches. Let's look at an example: solving a complex crossword puzzle. When the generator proposes a candidate word for 5 across, the evaluator checks whether the proposed letters match the existing intersecting letters on the board. If there's a conflict, the evaluator labels the step impossible, instantly telling the search controller to prune that branch and try another candidate word.
Moving on to our next question: what are the computational cost and latency implications of tree of thoughts in production?
While tree of thoughts offers incredible reasoning capabilities, we must talk about the elephant in the room for AI engineers: computational cost and latency. When you transition from standard zero-shot prompting or simple chain of thought to tree of thoughts, your API calls increase exponentially. Consider a standard CoT search with a depth of 4 and a beam width of 3. To explore this tree, the system might need to make 12 or more generation calls and over 36 separate evaluation calls for a single user query. In production terms, this means token consumption and financial cost can spike by 50x to 100x per request. Response times skyrocket from sub-second delays to 30, 45, or even 60 seconds. Because of these trade-offs, CoT is completely unsuitable for interactive user-facing web apps like real-time chatbots where users expect instantaneous feedback. Instead, CoT belongs in back-end, asynchronous pipelines for high-value tasks where quality strictly trumps speed. As a concrete real-world example, consider an automated enterprise tool evaluating custom software system designs. A single complex query might analyze 30 different tree nodes, taking 45 seconds to compute and incurring $5 in API charges. For a critical infrastructure decision, $5 and 45 seconds is an incredible bargain, but for a consumer chat app, it would be a complete non-starter.
Moving on to our next question: how does tree of thoughts compare to traditional search algorithms like A** or Monte Carlo tree search, MCTS?
To truly appreciate tree of thoughts, it helps to contrast it with classical computer science search algorithms like A* or Monte Carlo tree search, commonly known as MCTS. Algorithms like MCTS powered historic milestones like AlphaGo. However, classical search algorithms have a major limitation: they depend on rigid mathematical heuristic functions and hard-coded state simulators. MCTS works brilliantly for chess or Go because the rules are deterministic and easy to code into a simulator. But how do you write a mathematical heuristic for writing an essay, refactoring code, or designing a business strategy? You can't. This is where CoT bridges the gap. CoT replaces hard-coded math heuristics with generalized semantic evaluation performed by a large language model. In the CoT paradigm, the LLM wears two hats. It serves as the world simulator by generating potential next steps, and it serves as the heuristic evaluator by rating those steps in natural language. This means we can now bring the rigorous tree search mechanics of MCTS into open-ended natural language domains. For instance, consider exploring alternative software architecture options or proving complex mathematical theorems. An enterprise setup can run MCTS where state transitions and branch scores are calculated by an LLM evaluating system trade-offs. CoT doesn't throw away classical computer science search, it enriches it with semantic intelligence.
Moving on to our next question: What real-world engineering problems, e.g. code refactoring, complex planning, require CoT over standard CoT?
Not every prompt engineering task needs tree of thoughts. In fact, using it for simple tasks is a waste of time and money. So when should an engineer actually reach for CoT over standard chain of thought? The answer comes down to two key factors: a high combinatorial search space and the essential need for backtracking. Standard linear CoT works fine when step 1 naturally leads to step 2 and step 3. But in complex domain problems, an early mistake can trap the model in a local optimum, leading to a completely invalid result. CoT is designed specifically for problems where early mistakes cause catastrophic downstream failures and where you must test multiple hypothesis trees. Key engineering use cases include automated drug molecule discovery, strategic supply chain route planning, automated formal logic proving, and large-scale software refactoring. Let's walk through a concrete software engineering example: refactoring a legacy 5,000-line C++ module into modern Rust. If you throw this into a linear CoT prompt, the model will start converting line by line, make an incorrect memory ownership assumption on line 50, and produce completely broken Rust code by the end. With CoT, the system decomposes the refactoring into architectural submodules, generates candidate ownership models, and tests intermediate Rust compilation at each node. If a dependency path fails to compile, CoT backtracks to try an alternative module structure, guaranteeing a functional final refactor.
Moving on to our next question: when should an enterprise choose CoT prompting versus building a full multi-agent system, e.g. Crew AI?
A common architectural question enterprise teams ask is, should we use tree of thoughts prompting, or should we build a multi-agent system using frameworks like Crew AI or AutoGen? To decide, you need to understand the structural difference between an algorithmic search strategy and an organizational workflow framework. Tree of thoughts is an algorithmic search strategy. It is designed for a single core model systematically tackling a focused, complex reasoning problem where exploring multiple paths, scoring states, and backtracking is necessary. On the other hand, multi-agent systems are organizational workflow frameworks. They excel when a business process requires distinct specialized personas, like a researcher, a writer, and a code reviewer, who collaborate asynchronously, pass tasks back and forth, and call external software tools and APIs. A common mistake is building an overly complex 5-agent system with heavy orchestration overhead when what you really needed was a simple Python search loop using CoT over a single model. Let me highlight a clear contrast. If your task is solving a 50-variable constraint satisfaction logic puzzle, choose Tree of Thoughts. It systematically explores the state space and backtracks efficiently. But if your task is launching an automated marketing campaign, where one agent conducts web research, another drafts copy, and a third calls an image API, choose a multi-agent system. Understanding this distinction saves months of architectural rework.
Excellent. You've completed Chain of Thought Prompting, Part 4, Tree of Thoughts and Systematic Search. In the next video, we'll dive deeper into using one-shot prompting to enforce strict JSON and XML outputs for API integrations. If you found this video helpful, please like, share, subscribe to SHR Trinity, and press the notification bell so you never miss our upcoming AI interview preparation videos. Thank you for watching. See you in the next video.